Imagine you're standing in your kitchen, getting ready to cook something notoriously stubborn. Like maybe it's a really tough bone-in cut of meat or, a complex fibrous stew that usually requires you to just baby it on the stove all Sunday afternoon.
Oh yeah, the kind of meal that takes your whole day.
Right. So you prep your ingredients, you lock the lid on your pot, you turn the heat up to high, and then almost immediately you turn the stove completely off. You just walk away.
Which goes against every culinary instinct we have.
Exactly. But when you come back an hour later, that tough bone-in ingredient is perfectly tender. The flavors are fully developed and the meal is completely done. I mean, it sounds like a gimmick or maybe just a really bad recipe that leaves you with raw meat, but it's an actual documented technique called 0-minute cooking.
It completely contradicts how we're taught to cook
Mm.
because we are so conditioned to associate long, sustained application of heat with tenderizing tough foods.
Right, like if you want it
Yeah.
soft, you boil it forever.
Yeah, you boil it for hours. But what we are looking at here isn't a culinary parlor trick. It's the result of some very extreme, very precise applied physics that fundamentally changes the environment the food is sitting in.
And today, our deep dive is looking at the hardcore science making that possible. We're unpacking a comprehensive product research report on a piece of Japanese culinary engineering called the Zero Vitality Pan.
Made by Asahi light metal. Yeah.
Right, and this isn't some niche gadget. The sources note they've sold over 3.14 million units in Japan alone. So we are going to explore the intersection of thermodynamics, material science, and culinary biology to understand how a single piece of cookware essentially, well, hacks time.
Because honestly, calling this just a pressure cooker completely misses the mark.
Oh, totally.
To understand the engineering here, you really have to look at it as a high-efficiency household thermal utilization system. I mean, it's essentially a laboratory instrument adapted for a domestic stovetop.
I am so fascinated by the idea of an indestructible kitchen tool that can do this, but I'm looking at the numbers in this report and they are wild.
They really are.
Before we can understand what this pan does to a piece of food, we have to establish the physical environment it creates inside that sealed metal dome. So let's start with the baseline. When you or I boil a normal pot of water on the stove, what are the physical limits we're dealing with?
Well, you're dealing with standard atmospheric pressure. You don't feel it, but the weight of the Earth's atmosphere is constantly pressing down on you and, on the water in your pot.
Okay.
That standard pressure is about 101.3 kilopascals, or kPa. Under those normal conditions, the boiling point of water is capped at 100 degrees Celsius.
Wait, is that an absolute hard limit? Like, what if I take that pot of water and put it on a massive industrial jet engine burner? Does it still never go above 100 degrees?
The liquid water itself never exceeds 100 degrees, no.
Really?
Yeah, adding more heat energy just makes the water undergo the phase change into steam faster. The steam takes that extra energy and escapes into the room, so your liquid stays locked at 100.
Okay, got it.
But when you seal a vessel, that steam is trapped. It fills the space, and as it continues to heat up and expand, the pressure inside the vessel rises. And here is the foundational thermodynamic principle. As pressure rises, the boiling point of water rises with it.
Because it's pushing back down on the liquid.
Exactly. Because there is more pressure pushing down on the liquid, the water molecules need way more energy to break free and become a gas.
So the ceiling basically goes up. If I use a standard off-the-shelf pressure cooker from a big box store, how much am I raising that ceiling?
Most standard pressure cookers add about 70 to 100 kPa of pressure to the environment. That elevates your cooking temperature inside the pot to maybe 115 or 120 degrees Celsius.
Okay, so a decent bump.
Yeah, but the Zero Vitality Pan pushes that internal pressure to a staggering 146 kPa.
Wow.
When you add that to the baseline atmospheric pressure we just talked about, you're looking at about 2.4 atmospheres of total pressure inside that pot.
I want to ground that number for the listener because 2.4 atmospheres is intense. That is roughly the equivalent of the physical pressure you'd feel if you were diving like 45 feet underwater.
It's a tremendous amount of force. It actually sits right at the absolute limit of domestic safety regulations in Japan.
I bet.
And under that extreme 2.4 atmosphere environment, the boiling point of the water inside elevates to 128 degrees Celsius.
Okay, 128 degrees versus a standard pressure cooker hitting 115 or 120. I mean, on paper, an 8 to 13 degree difference sounds negligible.
It does, yeah.
If the weather outside changes by 8 degrees, I might not even change my jacket. So why does this make such a massive difference in a pot?
Because we aren't talking about ambient weather, We are talking about thermochemistry.
Ah, right.
The report compares the zero vitality pan to premium European competitors. Fizzler, for example, operates around 75 kPa, which gives you about 116 degrees. A domestic Japanese rival like Wonder Chef hits 140 kPa and 126 degrees.
Still short of the 128.
Exactly. To understand why those extra few degrees up to 128 are the secret sauce, the source material points us to the Arrhenius equation.
Okay, let's get into the chemistry of it. How does the Arrhenius equation explain what seems like a really small temperature jump?
So the Arrhenius equation calculates the speed of chemical reactions. It proves that the relationship between temperature and reaction speed is not linear. It's exponential.
Exponential.
Imagine molecules in your food needing to cross a certain energy threshold, like an activation energy, to break down and cook. At standard boiling, only a small fraction of molecules have enough energy to get over that hurdle at any given moment.
Right.
But as you increase the temperature, the number of molecules that suddenly have enough energy to cross that threshold doesn't just tick up slightly, it explodes.
So it's not like driving a car where pressing the gas a little gives you a smooth, steady increase in speed. It's more like a dam breaking.
That's a great way to visualize it.
Yeah.
A general rule of thumb in chemistry is that for every 10 degrees Celsius increase, the rate of a chemical reaction roughly doubles.
Doubles. Wow.
Yeah, so jumping from a standard pressure cooker's 115 degrees up to 128 degrees means the thermal transfer and the chemical breakdown of the food happen exponentially faster.
It's essentially like having an industrial laboratory autoclave sitting on your kitchen stove.
Pretty much.
You've engineered an environment so volatile that the normal rules of cooking time just collapse. But this brings me back to the 0-minute cooking concept.
Right, paradox.
Yeah, if I have an autoclave on my stove cooking exponentially fast, wouldn't the food just obliterate? If I put a stew in there, I'd expect it to turn into absolute mush.
And that is the trap most people fall into when thinking about high pressure.
Yeah.
It's where the specific mechanics of the 0-minute technique actually come in. You aren't maintaining that active heat source while the food is at 128 degrees.
Okay, so what do you do?
The pan uses a heavy pressure weight on the lid, a red weight specifically calibrated for this high pressure. You put the pan on the heat, and the moment the internal pressure reaches 146 kPa and the water hits 128 degrees, that heavy red weight starts aggressively jiggling and hissing.
Releasing steam.
Yeah, releasing a tiny bit of steam to prevent it from exceeding the limit.
Giving you a very loud physical auditory signal like, hey, turn me off.
Exactly. And the very second it starts doing that, you turn the stoves completely off. The active cooking time at maximum heat is literally 0 minutes.
But you don't open the pot.
No, you leave it alone. You are now relying entirely on the massive amount of residual thermal energy trapped inside that pressurized vessel. The food finishes cooking as the pot slowly, naturally depressurizes over, say, 20 to 30 minutes.
So it's coasting on its own momentum, like a controlled glide down from 128 degrees, rather than continuously blasting the food with heat that would tear it apart.
It uses the decay of the heat to gently finish the chemical reactions.
Let's look at the biological side of things, because the source material goes deep into a very specific culinary application for this thermal glide breaking down hard fish bones.
Oh, this is fascinating.
Yeah, if we have this extreme 128-degree environment coasting down, what is actually happening to that organic matter on a molecular level? Because turning a sharp fish bone into something edible seems biologically impossible.
Well, to understand how the pan achieves this, we need to strip away our everyday perception of what a bone is. We tend to think of bones as solid pieces of rock,
Right.
but they aren't. A bone is a complex biological matrix. You have hard, inorganic minerals, which are mostly calcium phosphate crystals. But those hard crystals are suspended within a flexible, mesh-like network of organic collagen fibers.
So the collagen is like the scaffolding. It's the netting holding the hard calcium gravel together.
Precisely. Now, if you boil a fish in a standard pot at 100 degrees, trying to break down that collagen scaffolding takes hours. The energy just isn't high enough to efficiently dismantle the proteins.
And what happens to the rest of the fish?
By the time you finally melt the collagen, the fish meat itself has been boiling for hours. The proteins in the muscle fibers seize up, squeeze out all their moisture, and you're left with dry, stringy, ruined fish meat floating in a cloudy broth.
So you win the battle against the bone, but you completely lose the fish.
Exactly. But at 128 degrees in the zero vitality pan, a process called rapid thermal hydrolysis takes over.
Thermal hydrolysis, okay.
Yeah, collagen is structured as a tightly wound triple helix of proteins. It's incredibly strong, sort of like a nautical rope. But at 128 degrees, combined with the presence of trapped water vapor, the water molecules act like little wedges.
Wow.
The thermal energy is so high that it violently forces those triple helix structures to unwind and snap almost instantly.
And once that nautical rope is cut, the scaffolding is gone.
The calcium crystals literally crumble. They have nothing binding them together anymore. The entire structural integrity of the bone collapses. It becomes incredibly soft, essentially turning into a paste when you chew it.
That's insane.
And because the total active cooking time was so short, remember, we turned the heat off. The meat of the fish was only subjected to that extreme environment for a brief, controlled duration.
Right, the 0 minutes.
Yeah, so the muscle fibers don't have time to fully seize up, which means the fish stays perfectly moist and juicy.
The sources actually give us the specific pressure times required for different types of fish, and the data is pretty staggering. Like, if you're cooking sardines, which have relatively soft bones anyway, it takes just 5 to 10 minutes of residual heat coasting, and the small bones just vanish.
They just dissolve, yeah.
For a mackerel, which has that thick, stubborn center spine, you give it 15 to 20 minutes of resting time, and the spine becomes exactly like what you'd find in a tin of canned fish. You just chew right through it.
And the report highlights sea bream, or tai, as the ultimate test. The skull and collarbones of a sea bream are incredibly hard, dense, and sharp.
Oh, yeah, you don't mess with those.
In traditional cooking, they are purely a hazard. But after 25 to 30 minutes of natural depressurization in this pan, even those massive bones become completely soft and safe to eat.
When you think about the implications for you, the listener, it's a massive shift in how you consume food. You are extracting deep nutrition, pulling calcium and minerals directly from the bones, while simultaneously eliminating food waste.
Exactly.
We're not throwing a third of the fish in the trash anymore. It's a perfect alignment of nutritional science and sustainability.
It is, but achieving that alignment requires a physical vessel capable of actually containing it. I mean, if you have essentially a pressure bomb sitting on your stove at 2.4 atmospheres, cooling down slowly, you can't just put a tight lid on a cheap tin pot and hope for the best.
I would assume not. If the lid is, say, 10 inches across, 2.4 atmospheres means you have hundreds of pounds of physical force pushing outward on that metal. So how does the physical vessel safely contain that while also managing the heat?
This is where the material science becomes the hero of the story. The manufacturer utilizes what they call a stainless aluminum 5-layer clad steel structure.
Okay, 5 layers.
They are sandwiching different metals together to exploit their individual metallurgical properties. They use aluminum layers in the core. Aluminum is incredibly porous to heat. It has supreme thermal conductivity.
It grabs the heat fast.
It grabs the heat from the stove instantly, but aluminum is soft and it reacts poorly with acidic foods. So they wrap that aluminum core entirely in highly durable, corrosion-resistant stainless steel, specifically SUS 304 grade.
Let's clarify SUS 304 because I see that thrown around in high-end kitchenware a lot. Why does that specific grade of steel matter?
SUS 304 is an austenitic stainless steel, meaning it's alloyed with roughly 18% chromium and 8% nickel. That specific chemical makeup forms a passive microscopic layer on the surface of the metal that makes it exceptionally resistant to oxidation and corrosion. You can cook highly acidic foods like a concentrated tomato sauce or a vinegar-based stew at 128 degrees, and the acid will not pit or degrade the metal.
Okay, so it's a 5-layer metal sandwich that resists acid and grabs heat. But multi-layer clad pans are everywhere, right? Like you can buy a tri-ply pan at any department store. What makes this one functionally different?
The crucial competitive differentiator outlined in the report is the geometry of the cladding. Many competitors, even premium ones like Wonder Chef and Fissler, often only use that heavy multi-layer structure on the bottom of the pan where it touches the burner.
To save money.
To save weight and cost, yeah. The sides are just standard thinner steel. But the Zero Vitality pan maintains a full 2.5 millimeter thickness of that 5-layer clad steel throughout the entire body of the pot. Bottom, sides, all the way to the rim.
Oh, I see. It's the difference between wearing thick, insulated winter boots, but just a thin cotton t-shirt on your body, versus wearing a full-body thermal spacesuit.
Exactly the right visual. Because it's fully clad, the heat doesn't just hit the bottom and stop. It races up the aluminum core in the sides. The heat physically wraps around the food.
That makes sense.
This full-body cladding prevents localized scorching on the bottom, which is a notorious problem if you're using an induction or IH stove that blasts magnetic heat directly into the base. And more importantly, that thick 2.5 millimeter 5-layer wall maximizes thermal storage.
So it acts like a heat battery.
Yes, aluminum has a high specific heat capacity. It absorbs a massive amount of energy. Remember the zero-minute cooking technique?
Right, where we turn it off.
The entire process relies on you turning the stove off. You need the physical mass of the pot itself to hold on to enough thermal energy to finish cooking the food. The pot physically becomes the heat source.
But let's go back to my spacesuit analogy and that 2.4 atmospheres of pressure. Because if I'm wearing a pressurized spacesuit, my single biggest fear is a breach.
Naturally.
If we have hundreds of pounds of force pushing against this lid and I've turned my kitchen into a high-pressure lab, how do I know I'm not going to blow a hole in my ceiling?
Safety engineering is arguably the most critical aspect of the entire design because the consequences of a failure at 146 kPa are catastrophic.
Yeah, that would be bad.
The report details a 5-tier fail-safe system engineered to ensure that an overpressurization explosion is mechanically impossible. It goes far beyond just a strong locking lid.
Walk me through the sequence. Like if something goes wrong, how does the pan catch it?
It starts with user awareness. There is a visual internal pressure pin that physically pops up so you can see when the interior is pressurized.
Okay.
Attached to that is a physical lock lever that prevents you from forcing the lid open while that pressure exists. You literally cannot turn the handle.
Which is standard and great, assuming the exhaust valves are working. But what if I'm cooking something thick, like split pea soup, and a piece of food boils up and entirely clogs the main pressure nozzle?
They've engineered mechanical redundancies specifically for that scenario. There are 2 completely separate safety valve rubbers hidden under the lid. If the main nozzle clogs, the building internal pressure pushes a small silicone ball out of the first safety valve, venting the steam downward safely.
Okay, that's smart.
And if that somehow fails, say, the entire lid is coated in scorched food and pressure continues to build toward a dangerous threshold, the entire second rubber valve is designed to just blow out entirely.
It just pops.
It sacrifices itself, creating a massive exhaust hole to dump the pressure before the structural integrity of the steel pot is ever compromised.
Okay, so it fails gracefully. But what about human error? What if I'm rushing, I put the lid on, but I don't twist it all the way into the locked position, and then I turn the heat on high? I've essentially created a leaky, unstable pressure vessel.
That's where the most ingenious mechanical failsafe comes in. It's called the packing safety rod.
The packing safety rod.
Yeah, if the lid isn't completely perfectly rotated into the final locked position, a small metal rod actively pushes the silicone sealing ring, the packing, out of its groove. It intentionally forces a gap between the lid and the pot.
It proactively ruins the seal.
Exactly.
So if I mess up, the pot just refuses to work.
It is physically impossible for the pot to build any pressure in the first place. The steam just escapes out the side from minute 1. It's a completely foolproof mechanism to prevent human error from turning into a thermodynamic hazard.
The pot acts as a secondary supervisor, double-checking your work before it allows the physics to take over. Now, because of this robust 5-layer steel construction, the SUS 304 grade, and all these fail-safes, Asahi Light Metal offers an absolutely unheard-of 30-year warranty on the body of the pan.
Which is incredible.
Right. And when I read that in the sources, I thought, amazing. Finally, a piece of consumer hardware that rejects planned obsolescence. But diving into the fine print reveals a really fascinating challenge regarding long-term product ownership.
It's a fascinating study in manufacturing economics. The company operates a service they call the Hospital for Pots, or Onabin no Buen. It's a localized circular economy setup.
How does that work?
If your pan gets damaged, or if you have one of their associated frying pans and the non-stick coating wears off after 10 years, you don't throw the heavy metal into a landfill. You send it back to the manufacturer, they mechanically repair it, they strip and recoat it, they polish it, and they send it back to you.
Which sounds like a utopian dream for a consumer. You buy one pan in your 20s and you use it until you retire.
It does. The 30-year guarantee covers the structural integrity of that thick, clad steel body.
Yeah.
But here's the catch that the report highlights. The guarantee does not cover the consumable parts. In a pressure cooker, no matter how well engineered the steel is, relies entirely on a perishable component to function the silicone packing ring inside the lid that creates the airtight seal.
And we just established that this ring lives in an environment of 128 degrees Celsius and 2.4 atmospheres.
Right, and silicone, while durable, is a polymer. When exposed to repeated thermal cycling at 128 degrees, the siloxane backbone of the rubber undergoes compression set and cross-linking. It slowly degrades.
So it cooks itself.
Pretty much. It hardens, it loses its elasticity, and it develops microcracks. The manufacturer explicitly states this ring must be replaced every 1 to 2 years to maintain safety and function.
I see where you're going with that, and it's a massive paradox. It's a brilliant business model for selling replacement parts, but it is a potential trap for you, the listener. You think you are buying a buy-it-for-life product, but its actual lifespan is entirely dictated by its weakest, cheapest, highly perishable component.
This is what the source material calls a critical second-order risk. The manufacturer guarantees they will provide spare parts for 10 years after a specific model is discontinued. But remember, the pot itself is guaranteed to last for 30 years. The math immediately breaks down.
The pot outlives its own supply chain.
The report documents actual cases of this happening, causing immense frustration for users. Take an older model in their lineup, the SW model.
Okay.
There are users out there with SW pots that are 15 or 20 years old. The 5-layer steel body is indestructible, it's in perfect condition, and could easily last another 20 years.
Right.
But because the manufacturer stopped making that model over 10 years ago, the specific $15 silicone gasket required to seal the lid is no longer manufactured anywhere on Earth.
Okay.
And without that exact proprietary silicone ring, the entire fail-safe pressurization system is void.
The consumables paradox.
Yeah.
A $300 piece of exquisite engineering, guaranteed for 3 decades, rendered completely obsolete by the absence of a $15 piece of rubber. It just becomes a really heavy, regular saucepan. It emphasizes a stark reality. If you are going to invest in a lifetime appliance, you have to adopt a different mindset. You have to immediately become your own supply chain manager. If you buy a pot meant to last 30 years, you need to buy 10 silicone rings on day 1 and store them in a cool, dark drawer, or the 30-year warranty on the metal means nothing.
It challenges the very definition of what sustainable consumerism actually looks like in practice.
So to synthesize this whole journey, what we are looking at with the Zero Vitality Pan isn't just a pot. It's a highly calibrated laboratory instrument for your kitchen. By harnessing the Arrhenius equation, mastering 146 kPa of pressure, and safely managing 128-degree heat inside a 5-layer thermal battery, you can save immense amounts of cooking energy.
Absolutely.
You can unlock deep, otherwise inaccessible nutrition by literally melting the molecular scaffolding out of hard fish bones. And you can participate in an anti-throwaway culture, assuming you manage your perishable spare parts correctly.
And that tension brings up a broader, somewhat provocative philosophical question that I think is worth pondering for everyone. As we look toward a future where we desperately need to engineer consumer products with true 30-year lifespans to stop filling landfills, how is society going to solve this consumables bottleneck?
That's a tough question.
Will the kitchen of the near future require us to keep open-source 3D printers and liquid silicone molds on hand? Will consumers have to illegally pirate the CAD files for a manufacturer's gasket just so we can manufacture our own replacement parts to maintain our heirloom appliances when the original companies inevitably discontinue them?
It really makes you look at the economics of your kitchen drawers a little differently. You might need a server rack next to your stove just to keep your pots running. The next time you turn the heat on high, just to turn it right back off again, remember exactly how much thermodynamics, material science, and manufacturing foresight is trapped under that lid.